So we are here today to talk about a pretty interesting problem. There's a lot of solutions floating around this conference, but there's a big problem that we would like to discuss with you. It's not small, it's actually rather large. But how big of a problem is this? So there is a $700 billion problem in AI right now that most people aren't really talking about, which is rather interesting given that it's fairly obvious. Now, before we get into this, what's interesting to note is that over the past decade, the amount of research being done in the AI space has nearly tripled. Now, this doesn't include 2023, 2024, so that number is probably even higher. So a massive amount of influx moving in, even pre-ChatGPT and LLMs. Now, of that research that was done, the research dedicated to software development, the majority of it is all around code generation. So the vast majority, about 56% of all the research done in the past 10 years that's in the software space, software creation space, has been done for code generation. And that's interesting. That's actually really interesting. You know, the next fast follow is around maintenance. The next one's around QA. How do we keep what we build up and running? How do we check it? But again, the vast majority is around generating code. And the question is why is everyone so focused on generating code? Why is generating code so heavily researched in, heavily funded? And why is that? Is it because it's the cool one? We think that that's maybe the main problem where we're trying to help automate how to get software out there faster. But it's interesting. It's an interesting problem because we know that about 70% of software projects fail. And by failure, we mean that they go over budget, over timelines, they don't meet client expectations. So a large portion of these projects that we're looking to build don't even ever succeed. So why are we looking to generate code for a failing process and or product? And again, the 700 billion is based on roughly $1 trillion spend in 2024. And of those that fail, this is actually the really interesting part of all of this, is that of those that fail, roughly 78% of those are due to poor requirements. It's not because developers aren't great. It's not because the tooling's not there. It's not because we can't get access to individuals. It's because we can't even get out of our heads what we're trying to build. This is a massive problem. It's not being addressed enough. And so this problem alone of simply failing software projects due to requirement is about a $546 billion issue. And what's great about that, and what is really intriguing about that, is that there is a lot of empirical evidence showing that requirements is the leading cause of successful projects. So why again, is no one really looking at this? And so it begs the question that if attention is all you need, why is nobody paying attention? Luckily we are. So I'm Corey. I lead all the research here at Crowdbotics. And here we are really interested in this problem, really interested in how do you capture ideas into a way that makes software teams set up to be successful. And we're focused on this from two different areas. The first is what we call requirements encoding. So this is how do you take natural language, how do you take an idea and turn those into requirements that code can be generated on, code that can be ran on a Venn diagram machine. And notice I say code generated. We don't care who does it, just that code can be generated successfully and the idea is captured appropriately. The second side of that is what we call requirements decoding. So this is how do you take large existing legacy code bases and abstract out their meaning and what do they do at either a human readable level or at some higher level that you can begin to understand. And when I say large code bases, I mean 10 million lines plus, big, hairy beasts that a lot of enterprises and a lot of big companies face. And we'll walk through a little bit of these first. So the first one around requirements decoding is actually a really interesting problem. The way that we do this is fairly similar to how humans work. We look to take a natural language statement, some idea, some concept, some problem that someone has, and be able to slowly chunk that and then break it down. Following a similar pattern to how kind of most scoping exercises go, looking at the epics, high level conceptually, what does that mean? How do you start to break those down into user stories and then further decompose those down into things like user personas, potential API endpoints, and many others. Now, this problem has been extremely hard to do, mostly because of context windows and sizes of the projects that we're looking to tackle. Building and looking to build tic-tac-toe apps is really cool, but if you are an enterprise looking to build a large-scale piece of software that might have 10, 20, 30 devs working on it, being able to chunk down that idea into these lower level requirements becomes actually really difficult, even with a million line context. And what's interesting about all of this too is that now that we have this understanding and it is captured in a model context, that context becomes extensible. And when you make context extensible, you're able to do a lot of really, really interesting and cool things. The tool itself is really great to use. Our software is super easy, super intuitive to use. You simply go in and be able to put in a natural language statement of what you're looking to build. You can upload documents, upload anything else that was done during that initial kind of brainstorming or gathering session. From there, the tool and the model is able to take that and chunk it and break it down into extremely low-level requirements, things that can be fed into tools like Workspace, into tools and things like Copilot that make them better. So you can see here we've broken it down. We have things like features that get put into descriptions, acceptance criteria, user personas, technical recommendations, right? And you get all of this right at your fingertips from simply a few lines describe what you want to do. Our analyze here goes and actually looks a lot deeper. So based on this individual feature itself, what are some things that we might want to look out for on the front end? What are some things on the back end, potential API endpoints that might need to be designed? All of this is being put there to set developers up for success. We want to make sure that at the onset, we are capturing all of the requirements that need to be done. On the requirements decoding side, this part's actually pretty interesting. My demo, my Lego thing, he passed it. So on the requirements decoding side, this is where we actually take these large code bases and look to find ways to abstract them out into requirements, because human language and human understanding is some of the toughest parts about managing extremely large projects. And the way that we do this, because we faced a number of challenges, again, in dealing with the size of what these code bases are, is that we use a multi-agent kind of setup. Where at the beginning side of it, we have one agent that's set up to kind of look to understand context. So this is things that are about the existing platform that we may know. It could be legacy documentation, things that are probably outdone, different ways that clients like to document and categorize their requirements. We have another agent we call our codex agent. This agent goes in and actually does all of like the chunking and understanding and assimilating of code from the bottom up. So we start all the way line by line, up to features, up to classes, and then are able to abstract that and keep it all here. From there, we have an orchestrator that basically manages both of these and then goes into a domain agent. So this domain agent basically leverages both of these back and forth to be able to say, okay, I understand here, how should it be documented based on what's already out there? We then have a discriminator or an evaluator that passes into next, that is able to feed back and ask questions to our context and also to our codex agent. Finally, outputting it into some great artifacts, things like data models, dependency models between methods, variable tracing, code tracing, and a number of other things. So a quick demo of how this works is that you simply go in, create an app. You're able to access all of this directly from GitHub. So any existing GitHub repo you have, you can go and select it, and you simply hit next. And from there, again, all of this runs in the background, and will kind of create out your product requirements doc. And so you can see we've gone from natural language into a set of requirements, and we can also go from code back up into requirements. And this is being used a lot today in a number of different ways, which is really exciting. Doing things like rapid prototyping from the idea to requirement stage, doing things like modernization, being able to extend codex functionality and intelligence to other models. We'll talk a little bit more in a second. Now, all of this is great. Actually, all of this is really cool, and all of this has been really, really hard to build over the last few years. But AI itself is in a really interesting position. Like our current methodology has been, in order to get better model performance, we'll do a few things. One, we'll give it more data, and then two, we'll give it more compute. And this has been working. We have been shoveling cache and shoveling data into these frontier models to make them better and better and better. But in doing that, you set a natural ceiling. So the natural ceiling for what these models can accomplish. And we've seen some good advancements in things like chain of thought, doing reasoning with the 4.0, RAG, other kind of ways to make all of this work. But those are emergent properties, right? Those we call emergent properties or hobblers within the AI or LLM system. These are things that were not designed into the system at the onset, but we found out how to improve the performance by simply doing these. Another way to improve model performance is simply through sharing. Now, this is all really interesting because just a few days ago, like right down the streets, Noam Brown, who's one of the lead research scientists at OpenAI, made a great kind of claim that the transformer architecture that we're building all this on hasn't really changed since 2017. So how do we improve this? What are things that we can do today? What are low-lift solutions beyond things like chain of thought, beyond things like RAG, that can actually give us substantial improvements in space? And we looked at this and we said, well, we know a lot about what we're trying. We have a lot of context on the requirement. Like we know from a business layer what needs to be done. And there's a lot of great tools out there that can generate code. So what if we could just share our requirements in some way? Like what if we could just plug in our commercially available tool into another commercially available tool and see what happens? Do we get improvements out of these tools? And so, being a researcher, that's what we did. And we recently published a white paper on it as well, where we were looking at basically creating multi-agent configurations of commercially available products. Now, this is different because a lot of multi-agent setups have been studied in the academic sense. A lot of them are in the black box in companies like Anthropic, companies like OpenAI, but there's been little work on taking established, publicly available commercial tools and saying act as agents together, collaborate, and then does that actually provide some benefits to the base models themselves? And what we found was pretty astounding. So in this study, what we did was extend our business requirement model context into GitHub Copilot, specifically in their code suggestion features. And we thought, well, if Copilot knows a little bit more about what's going on the business side, then maybe it'll provide better suggestions. But being scientists, we had to try it, and what we found. And the findings were pretty compelling. So in that study, individuals using GitHub Copilot and Crowdbotics together, they saw about a 25% success increase in doing a task, right? So we ran this in a 4-hour study where the task took roughly 4 hours at the max to complete, and 25% more people were successful using these two together. Now, the really interesting part is that the code suggestion feature of GitHub Copilot improved by almost 14%. And this is 14% improvement without any additional data, any additional training, and no additional compute. By simply sharing knowledge between two models in the commercial space, we were able to get these massive gains and massive improvements. Now our system itself is available right now as a GitHub Copilot extension. So you're able to plug it into your IDE. You can start pulling context from a PRD, sharing that with GitHub Copilot. You're able to see these same results as well. So I invite everyone to please go try it out. It is a really, really cool tool, a really, really cool feature, and something that we are very proud of. And also, as far as roadmap, our core platform itself has a lot of interesting things coming out in the near future. So I beg all of you, if you leave here, to kind of ask yourself one question, is that if attention is all you need, what exactly are you paying attention to?